So before I start, there is of course a range of textbooks that I highly recommend reading and studying. Wikipedia and Google are in the end, right? They're very useful. But also there are some fundamental textbooks that cover many of the topics that I will be talking about. So the Szabo and Oslund book is referenced in quantum chemistry, Parr and Yan book, of course, in density functional theory. For more sort of practically inclined, there is a chemist guide to density functional theory. Actually on Friday, I will be giving another talk, actually Blackboard talk on theory of intermolecular interactions, which is something that is not widely studied in normal physics and chemistry curriculum. But Anthony Stone's book is really the reference that connects actually electronic structure methods and a theory of intermolecular interactions. And Kieron actually mentioned SAPT, symmetry adapted perturbation theory, which is a theory which actually connects electronic structure and intermolecular interactions. And I think personally, it's very important to also connect what we are doing, because we are interested in atomistic modeling, to really understanding different kinds of intermolecular interactions and how they contribute to observed phenomena in molecules and materials. Okay, so just to start very broadly, Kieron uses DFT to study his coffee, but that's not the only application of electronic structure. There are many more. For example, you can study polymers, for example, mechanical properties of polymers. And of course, a lot of those arise from a wide range of different intermolecular interactions, electrostatics, polarization, dispersion, and so on. You can design novel solar cells, or in general, optoelectronic materials. For this, you need excited state theory. Ground state is not enough. You can study pharmaceuticals, and I gave examples in my talk yesterday, right? How electronic structure theory really advances the field of pharmaceutical research, in particular formulation of novel drugs. And also there is a wide range of materials applications, for example, design of novel materials for turbines, and in general, understanding how nature uses intermolecular interactions to actually perform function, such as this famous animal gecko that can climb on walls and ceilings, and you see a lot of them in tropical parts of the world. For example, in Mexico, there's a lot of them, and they are pretty funny animals, and they use van der Waals interactions to actually perform their function. Okay, so I think a lot of you do some kind of computational either chemistry, physics, or material science. And of course, in this field of atomistic modeling, there is a long-held dream that we could really understand properties and functions of molecules and materials from first principles of quantum mechanics and statistical mechanics. And a dream scenario is something like this, that you could really solve the Schrodinger equation for a large enough system, and hopefully you can do it in this linear scaling. And Jian Feng mentioned this development of novel computational algorithms that allow to reduce the formal scaling of our methods. And of course, all of us need quite heavy computational resources in order to enable this large-scale simulations. And the real issue is how we combine accuracy and efficiency at the same time, right? And that's what a lot of talks will be concentrating, I think, during the whole program. Now, another thing why atomistic modeling or electronic structure is so important is because, of course, they form a basis of multiscale modeling hierarchy. Really, every method that goes beyond electronic structure, beyond quantum mechanics, let's say, classical force fields or machine learning force fields, coarse-grained models or continuum models based on differential equations, they in principle should be parameterized from the very beginning, from first principles of quantum mechanics. Okay, so let us start from the very basics. You've already seen the Schrodinger equation. I don't have to tell you too much. So this is just a single particle here with its kinetic energy, and it's in some potential. And the wave function principle, of course, depends on both spatial and temporal degrees of freedom. Now, as Kieron already said, there is no spin degrees of freedom, there is no relativity, no field-matter interaction. The next talk after my talk actually will concentrate on QED, so how do you go beyond this? However, for most molecules and materials, this Schrodinger equation generalized to a many-body system is, of course, a very good approximation. And that's why we use that as a standard model for chemistry and material science and a lot of physics. Okay, so what we typically do is we separate variables, right? So the wave function depends on spatial degrees of freedom and temporal degrees of freedom, so we can separate variables and then basically get rid of the temporal part by just writing a phase, right, of the wave function. So we have a product wave function between the spatial part and the temporal part that just looks like a phase factor. So, of course, this leads to this idea of stationary states, and we can expand the temporal behavior of a quantum mechanical systems in terms of stationary state, always if you have a complete basis. And so then the electron density, which we often use as a variable, becomes, of course, a time-independent solution. And, of course, each state would have its own electron density. Okay, so in the Schrodinger equation, of course, we have several things here, right? We have the Hamiltonian operator, we have the wave function, which is a 3n-dimensional object, and we have the energy. And of course, it's an eigenvalue equation, and so in principle, we have an infinite number of solutions, of stationary states. And the Hamiltonian is, again, consists of the kinetic energy plus potential energy, right? For the many-body system, you would have something like this. And when you solve the Schrodinger equation, well, you get the ground state energy, E0, and all the excited state. And you have, of course, bound excited states. You can have scattering states, right? And you then have continuum states, which look like plane waves, like solutions to the independent particle problem when the potential vanishes. Now, a few remarks about this. Wave functions, of course, are immensely complex objects. Once again, they are, if you have n nuclei and m electrons, you have 3 n plus m, 3 by n plus m degrees of freedom. And so expanding these wave functions is very difficult. Wave functions are also difficult to interpret for anything beyond 1 or perhaps 2 particle systems, and hence, we typically use coarse-grained representations like densities, so for square of the wave function, or other expectation values, right? Like, we can compute dipole moments, polarizabilities, and so on and so forth, and they all give us a bit different information on our quantum mechanical systems. The part of the complexity of quantum mechanics, of course, arises from the fact that you have commutators, which are not trivial. And so in classical mechanics, the commutator between kinetic and potential energy is 0. And so that means that particle kinetic energies are additive, and so the problem becomes very simple. But in quantum mechanics, this is no longer true. And so kinetic energy is a highly non-additive object, is a highly non-additive energy. And so it has a many-body nature. Now, when we coarse-grain quantum mechanics in terms of certain model for interatomic interactions, then it can often be expanded as an infinite power series, because we have quantum mechanics, right? Even for 2 atoms, you always have an infinite power series in terms of the geometrical degrees of freedom of the system. For 2 atoms, this is just, of course, a single distance, right? So it is a single degree of freedom. But for a many atom system, you would have angles, torsional angles, and in principle, it's a very complicated expression that involves the full geometry of the system. Now, there are quite many actually systems where you do have exact solutions of the Schrodinger equation. These are, of course, model systems or hydrogen atom. So if you have a single particle, you can solve the Schrodinger equation exactly for a free particle, for particle in the box, for harmonic and some anharmonic oscillators. You can solve it for the Dirac delta potential, for a hydrogen atom, for H2+, and so on. If you have 2 particles, you can solve the Schrodinger equation exactly for 2 non-interacting particles, of course, because it's just a superposition of solutions. You can also solve it for harmonium atom. This is an atom which has a harmonic potential from the nucleus, but a Coulomb interaction between the two electrons. And this also serves as a model actually for correlation effects, exchange and correlation effects in some density functionals. I think Kieron has also worked on this a bit, right? When we go beyond two particles, we get, of course, once again, we can solve the Schrodinger equation exactly for non-interacting particles, for effective one-dimensional Hamiltonians, for some versions of the Hubbard model. And, for example, we can solve the Schrodinger equation exactly for harmonic oscillators coupled with a dipole potential, for an arbitrary number of harmonic oscillators and arbitrary geometry of harmonic oscillators. And we use such models, for example, for describing long-range electron correlation of large systems. But as we all know, most realistic Hamiltonians, for example, a molecular Hamiltonian, does not have any known analytical or exact numerical solution. And so that's why we are sitting here today and discussing a wide zoo of different approximations to the solution of the Schrodinger equation. So in general, if you have a molecular solid-state system, well, then you have several nuclei typically, and you also have several electrons, right? So the simplest system is this one. So you have a single electron in the presence of two nuclei. So you have to define your reference frame here and the positions of the nuclei, and the electron interacts with both of these nuclei. So then you can write the full Hamiltonian. As you all know, right, you have the kinetic energy of the electrons, you have the kinetic energy of the nuclei, you have the electron-nuclear attraction energy, and then you have the repulsion, the Coulomb potential for the electrons and for the nuclei. So, of course, we use the Born-Oppenheim approximation. We kind of get rid effectively of nuclear kinetic energy, and we treat it in a classical way. And because the nuclei are much heavier than the electrons, then in principle we can do a factorization of the wave function in terms of the electronic and nuclear degrees of freedom, and the full wave function just becomes a product wave function. And typically, as I already said, you can treat the nuclear degrees of freedom classically because they are heavy, but you don't actually have to do it. So you can use, for example, path integral approaches to actually carry out quantum nuclear dynamics on a certain electronic potential energy surface. So this Born-Oppenheim approximation then introduces this concept of potential energy surface, right? If you do not use the Born-Oppenheim approximation, then potential energy surface does not exist, right? Because both nuclei and electrons are quantized and they are delocalized, so you cannot introduce this important concept. But often it's a good Born-Oppenheim approximation is good enough, not for everything, but for many applications in chemistry and physics. And so then basically, for a given system, you define nuclear coordinates, some initial nuclear coordinates, which can come from experiment or from a construction of a molecular solid just on a computer. You solve the Schrodinger equation for a given electronic subsystem. This gives you energies and forces or other properties, and then you repeat. Either you sample the coordinate, the potential energy surface using molecular dynamics, or path integral molecular dynamics, or Monte Carlo. So why is the solution of a Schrodinger equation complex, and why understanding the solution is complex is, for example, illustrated here. So what I'm showing here is a supramolecular system. It's a complex consisting of a fullerene molecule embedded in this ring molecule, which is a so-called cycloparaphenylene ring, and they interact. And you can compute the interaction wave function. In this case, I'm using a model of this coupled quantum harmonic oscillators, and I'm diagonalizing this Hamiltonian, and I get a normal mode representation that represents the interaction between the two molecules. And there are 3 n modes, where n is the number of atoms. And so what I'm doing here is I'm plotting one of those collective modes in terms of the displacements of the oscillators, in this case, from their normal position, from their center of mass. And as you see here, you get very complex displacement patterns, and there are 3 n of such patterns. For example, what you see is you have a quadrupolar kind of distortion of the wave function of the collective displacements. The wave function is a product of 3 n components. So you have a quadrupolar displacement on this fullerene molecule, and you have a ring-like current displacement of the oscillators on the cycloparaffin ring. You can generate the electron density that then corresponds to these displacements, and well, you get something like this. So the orange regions are depletion of the density, the blue regions are accumulation of the density, and so you can see that this, these density displacements are quite complex, and that's why understanding them is not a trivial task. If you go even to more interesting systems, which I actually used for example, photoelectronic applications, this is a hybrid, so-called hybrid organic and inorganic system. It's a molecule called copper phthalocyanine adsorbed on a silver 100 surface. And here again, I'm plotting an isosurface of the electron density displacement induced by the interaction of a molecule with the surface. Once again, you see quite a complicated pattern that includes depletion and accumulation of the electron density in different regions.
So when you say displacement, you mean just the change compared to when the molecule is not absorbed?
Yeah, that's right. So I'm separating the system, let's say, to infinity. So I'm taking away the surface, I'm taking away the molecule, and then I take the full system and I take this difference. It's a difference density. So it's also called the deformation density due to the interaction between the two objects. Okay. So, of course, there is a huge multitude of methods which we can use to approximate the exact solution of a Schrodinger equation. Kieron mentioned full CI, which is a method that is not really widely used any longer. It was used for very simple systems in the past. In fact, the best results we have for atoms come from full CI still. But today we don't use it as a practical method because full CI requires all excited determinants and then obtaining linear coefficients of all those excited determinants, even for a system with just a few electrons. In a reasonable basis set, one electron basis set, you get a number of determinants which scales quite a lot with the number of electrons, and so this is not a very practical method. So in practice, what we use in order to approximate solutions of the Schrodinger equation at the high level are so-called wave-function-based methods. And couple cluster, for example, the single, double, and perturbative triple excitations is considered in the quantum chemistry community as so-called gold standard because for small molecules, it often yields this widely sought chemical accuracy of 1 kcal per mole. But of course, we can go further. Density functional theory, as was already explained, is a workhorse method which is widely used for both molecules and materials. Typically, the semi-local and hybrid functionals or meta-GGAs have been becoming more widely used in the last few years. In addition, there is also a wide range of methods such as semi-empirical approaches which approximate wave function-based methods or density functional theory by dropping integrals, by approximating the Hamiltonian, and by introducing fitting parameters that allow to describe certain classes of systems. So these are not general methods, I would say. The generality are only obtained when you go to density functional theory in some sense. But nevertheless, those methods such as tight binding or semi-empirical quantum chemical Hamiltonians are actually quite interesting when it comes to describing a certain part of chemical space. For example, if you're interested in certain semiconductors, or if you're interested in organic molecules, you can often find a very reasonable parameterization of those methods that is also able to scale to thousands of atoms. And of course, at the very base of this hierarchy here, we have empirical potentials that in principle do not contain any explicit electronic degrees of freedom, and they are often also called mechanistic force fields. These are widely used for biomolecular simulations, as you might have heard from biochemistry and drug design and so on. Okay, so the simplest way to actually solve the Schrodinger equation is, if you don't know anything, is to just propose a certain form of the wave function. Now, of course, it's not so trivial to propose a form for the wave function, right, which would include some functional form multiplied by certain coefficients, which you optimize. And it's not trivial to propose a functional form because of the antisymmetry requirement for fermions. Even for 2 electrons, right, the simplest form that satisfies the antisymmetry requirement is a Hartree-Fock determinant, right, and that's already not so easy to deal with. But let's say if someone allowed you to propose such a form, and you have some creative inspiration, and you could write a form, an actual functional form for the wave function, then in principle, all you need to do is to optimize parameters and use the Rayleigh-Ritz variational principle, which in principle will allow you to go lower in energy. And if your wave function has a sufficiently sophisticated functional form, you can get to the ground state energy. Now, in fact, this has been lately attempted for example, by DeepMind and by Frank Noyes group with this Pauli-net and Fermi-net approaches that in principle propose a neural network solution to a wave function, and then you use the variational principle to optimize the parameters in that neural network architecture, and you get a solution to the Schrodinger equation like this. So this is something that actually people now, with the advent of neural networks, are trying to accomplish. And so the simplest ansatz that you can take for a wave function, for a many-body wave function, and this was already mentioned earlier today, is of course Hartree ansatz. So you propose a product wave function. So if I have a wave function for n particles, well, what I can do is just I introduce orbitals, and I propose that each orbital only depends on the coordinate of a single particle. Right? So this is a simple product. And in general, of course, such ansatz is exact when my Hamiltonian can be decomposed in single particle operators. So if you have free electrons, right, and free electrons, well, then this ansatz is of course exact because all I have is a product of plane wave solutions to free electron problem. But many-body problems in general, some many-body problems can be reduced to such a Hartree-type wave function by using a coordinate transformation. So the example of dipole-coupled harmonic oscillators, or in general bilinear Hamiltonians actually, you can always find a coordinate transformation that takes you into this functional form. And that's an exact solution of such a many-body problem. Unfortunately, for electrons, we don't know how to do it. In principle, such a solution might exist for electrons, but we don't know how it looks like. Right? So we cannot reduce to a Hartree theory. So the biggest challenge of Hartree-type wave functions is that it does not treat the fermionic nature of electrons, so it doesn't satisfy the antisymmetry requirement that in electronic wave functions should satisfy, which means that if you have 2 electrons Ri and Rj, you exchange their coordinates, the wave function should change sign. So then, of course, because of that, well, we know that determinants satisfy this criteria. If you exchange 2 columns or 2 rows in a determinant, your determinant changes sign. And so all we need to do is to normalize it properly by this factor and introduce n molecular orbitals and write the wave function as this Hartree-Fock determinant. Then, once we have this, all we need to do is to minimize the wave function subject to orbital orthonormalization and the fact that the wave function has to recover the correct constant n. That's why we introduce this normalization factor here. So again, you can solve this since the Hamiltonian depends on the orbitals. You get a self-consistent solution, and so what you do is you initialize atomic orbitals, you solve, you find new orbitals, and you continue this. So you evaluate this Hamiltonian, and you continue this until convergence. So something that is often not appreciated, I think, is just thinking of the scaling of the energy. So how much of the total electronic energy you recover at different levels of electronic structure theory. So something that is quite, I would say, a bit strange even, right? That Hartree-Fock theory captures, for, again, single reference systems and so on, captures 98% of the electronic energy. And so just given perturbative arguments, you would think that the missing 2% is not as important. But if you use Hartree-Fock theory, for example, to compute the binding energy of argon dimer, it would be unbound. Right? So it would be physically wrong. Right? We know that noble gases and any closed shell molecules bind. Right? And so at Hartree-Fock level, they are unbound. So it means that something is missing, and of course what is missing is correlation energy. At least that's how it's defined in the quantum chemistry community. There are many definitions, again, as we discussed in the morning. But in the chemistry, in the quantum chemistry community, what is missing from Hartree-Fock, so the difference between the exact electronic energy and the Hartree-Fock energy is called the correlation energy. And by definition, it's stabilizing energy. Okay, so it always has a negative sign. So Hartree-Fock is an upper bound for the total energy. DFT is not, by the way. Right? So DFT does not obey variational principle. In terms of the exact solution of a Schrodinger equation. So now Hartree-Fock is really the base for what is called post-Hartree-Fock quantum chemical approaches, including Mollet-Placid perturbation theory, coupled cluster theory, configuration interaction, random phase approximation, or quantum Monte Carlo. Hartree-Fock is still an effective single particle theory, which means that you can write the solution in terms of n single particle equations. So you have the Fock operator, you have orbitals, and you have orbital energies. And this is widely loved by chemists because you can analyze those orbitals, and you can actually, in certain situations, you can prove theorems, such as Koopman's theorem, for example, in terms of the ionization potential, electron affinity, and the Hartree-Fock HOMO-LUMO orbitals. And so you can actually use those orbital levels to sometimes compare to experiments and to interpret experiments. Okay, so even if Hartree-Fock recovers 90%, 98% roughly of the total electronic energy, this 2 missing percent is extremely important, and it's called the correlation energy. It's a fundamental part of the electronic energy. It's responsible for things like van der Waals interactions. It's responsible for cohesion in a wide range of molecules and materials. And so without correlation energy, you are, in most cases, you are completely lost. And you can introduce now, based on Hartree-Fock, a new hierarchy, a quantum chemistry hierarchy, where you have a Hartree theory. You then go to Hartree-Fock theory, to Mollet-Placid perturbation theory, and random phase approximation, which is nothing else but an infinite order perturbation theory. Then you have coupled cluster ansatz and configuration interaction, and up to full CI, which corresponds to, in a full basis, corresponds to the exact solution of a Schrodinger equation. So what is the idea behind this hierarchy? So beyond Hartree-Fock, right? So at Hartree-Fock theory, you only use the occupied orbitals, or spin orbitals in general, to define your energy. Now, of course, in order to solve the Hartree-Fock equations, you typically introduce a basis, and these basis functions, you start with atomic orbitals, and then you form molecular orbitals from those, as superposition, as linear combinations of those atomic orbitals. And so you have, in general, more orbitals than you have electrons. And so this means that even in a Hartree-Fock calculation, you have occupied orbitals and virtual orbitals, so unoccupied orbitals. But in the energy expression, those virtual spin orbitals in general are not used in a Hartree-Fock. Okay, so they are not occupied. The occupations are 0. And the occupation of the occupied orbitals is 1, right, if you have spin orbitals. So the idea here is, of course, that you have your quantum mechanical system, you have uncertainty principle, or you can reinterpret it as the fact that vacuum fluctuates. And so the system prefers to lower its energy by doing virtual excitations from the occupied orbitals to unoccupied orbitals. And that's what is the basis for electron correlation. So the simplest method to include electron correlation is given by multiplexed perturbation theory. Lin actually spent quite some time talking about this yesterday. And so you have this expression, so you define a Hamiltonian as in two parts. So you define a perturbation Hamiltonian, right? Which is the electronic Hamiltonian minus what you already have at the Hartree-Fock level. Okay? And so in general, you have the Coulomb, the electron-electron Coulomb potential, and you subtract from it the Hartree part. This gives you essentially electrostatics, and the exchange part. Okay? So once again, as Kieron said, you have these two integrals because you can exchange particles between orbitals. And so you have to subtract that because that's from the full Coulomb potential, because that's what you already have, all those effects in a Hartree-Fock wavefunction. And now you use this perturbing Hamiltonian in a perturbation theory expression, and at the second order you get this term here, which is called the multiplexed second order perturbation theory term. So your total energy at the MP2 level is Hartree-Fock energy plus this perturbation theory term. And its interpretation is quite simple. So you have occupied orbitals, ij, you have unoccupied orbitals, ab, and you are doing transitions between them. And of course, the transition goes one way and it goes back. And that's why you have square in the numerator here. Okay? So essentially, electrons excite and de-excite. Right? And this term contributes to the ground state energy. Right? Although we are doing excitations, but we are just computing the contribution of those virtual excitations to the ground state correlation energy. And in the denominator, you exactly represent this process. Okay? So you have sum of the ground state, of the occupied minus unoccupied. Or well, vice versa. In this case, these are the unoccupied orbitals, these are occupied.
I think you might have too many stars.
Yeah, that's right. There should be only 2 stars, yeah. If they're real, they are often real in the molecular system, yeah. Yeah, I have too many stars here. There should be just 2, yeah. So there's a question?
Hi. I have a naive question regarding this virtual excitation. Are they similar to considering instead of having just in the ground state that just there are certain orbitals that are occupied, to have all the orbitals occupied with certain probability, which the maybe the most probability is for the orbitals that we call occupied, but the other orbitals have a really small probability to also being occupied. I mean, conceptually similar to path integral formalism, that we have all the passes, but it's the least action path, which is kind of the most significant. So is it similar, this kind of virtual excitation, the idea is similar?
Yeah, that's a good question. But you are bringing the question of interpretation of the correlation energy, right? Of the electron correlation energy. And so in this perturbative picture, you cannot really interpret it like this, right? In a perturbative picture, all you are saying is you have the full Hamiltonian, you did an approximate solution given by Hartree-Fock, and now you are taking the difference, right? So you are defining some H prime Hamiltonian, and you are applying it to second order of perturbation theory. But if you go to non-perturbative methods, for example, there is density matrix functional theory and so on, what you get is exactly what you are saying, that there are occupation numbers of ground state and excited states that are not just 1 or 0, but they can actually be fractional occupation numbers. And in that case, what you are saying is correct, right? That you can think of this as if the the excited states of my system had some effective occupation numbers. But I would not really consider, this auxiliary picture is correct, but let's say it's helpful. And some methods for correlation energy are based on this idea as well. But again, perturbation theory I would not interpret like this, okay? Because these excitations, once again, you excite and you de-excite, and you go always, you end in the ground state.
Thank you.
Any other questions?
So what do you call this term VH minus VX? What do you call that? The difference?
So this is the Hartree. So this is the term that you already have in your Hartree-Fock calculation. So this is the Hartree energy. It's essentially the electrostatic energy. And this is the exchange energy. So this is the non-classical part of the Hartree-Fock Hamiltonian.
And the difference has a meaning, has a physical meaning? Just subtracting.
It's just the Hartree-Fock.
Minus the, okay.
So you can, this minus here, there's nothing about this minus which is important. You can write a plus and you can incorporate the minus in. So it's just the definition of the integrals. So don't interpret this minus as anything that is relevant. Okay, so as Lynn said, right, so in order to compute this matrix element here, which corresponds to this excitation process, well, you need to know the Hartree-Fock orbitals, and you just compute this this excitation term, the excitation, the matrix element of the Coulomb operator corresponding to these excitations. So this is, so you can take perturbation theory to higher orders. MP2 is not the end of it. You can do MP3, you can do MP4, and you can do MP infinity, which essentially corresponds to the random phase approximation. But actually, there is no guarantee that perturbation theory converges. So the first few terms converge pretty well. But for many systems, you start seeing divergence at higher levels of perturbation theory. And for that reason, Moley-Placid perturbation theory is not widely used beyond MP2. Some people go to MP4 level. But it's not, again, a practical theory in many cases. So in order to, the largest challenge of perturbation theory is the fact that you only have,
Something. So there seems to be some revival of interest in MP3. MP4 I haven't seen. MP3 just in the past few years from Gordon's group, some other people's group. Can you comment on those?
Yeah. So basically, so if you look at the convergence of perturbation theory, you typically have oscillations, right? And at some point you have divergence. And what is observed often, right, is that in order to get something that approximates MP4, you can combine MP2 and MP3 with certain fitting coefficients. And so there is this theory in quantum chemistry which people call MP2.5, which is nothing else but a combination of MP2 and MP3 with weighting factors. And that's what people have pursued quite a bit. That originally came from the group of Pavel Hopsa and Stefan Grimme, and then Martin Head Gordon has also been recently playing with these terms. So it seems to work well for small organic molecules and for intermolecular interactions between small molecules. And that's why there has been a revival of looking at how you combine different low-order perturbation theories. But I don't think it's a very general approach. So the missing physics is really the screening physics, right? So these perturbation theory terms are, I would call, they are unscreened, right? So you have, you excite, but when you excite, all the other electrons in your system screen this excitation, right? And so when your system is, say, beyond benzene, and even in benzene, right, those screening effects are pretty large. And for that reason, instead of doing perturbation theory term by term, you prefer to go to an infinite order perturbation theory from the get-go, doing RPA or coupled cluster theory, right? Which are, of course, related. So that's the main problem in MP2. So if you have two particles, right, and one of them excites, another one excites, so those excitations are unscreened. So nothing happens to all the other electrons in your system, right? So it's as if you just have two electrons, two orbitals, right? And you throw away all the other parts of your system and you compute directly the correlation energies between these two electrons as if nothing else existed in your system. And that's, of course, physically incorrect. So when one part of your system excites, all the other parts respond. Right? The simplest way of thinking about this is just a spin glass system. Right? If you change one spin, all the other spins will rotate in order to compensate the field that comes from this spin. Right? The same happens if you have dipoles, right? And they form an electric field, and you change the polarization of your system at one point, all the electric field will basically try to close and compensate the polarization effect. Right? And so this is what is called screening in general, in physics at least. And these screening effects are included correctly at infinite order of perturbation theory. And so coupled cluster theory is one example of it. It's more general than just infinite order perturbation theory. But the main idea is that you take a zero sort of wave function, in this case this is a Hartree-Fock wave function, and you apply an exponential operator to it. And the exponential operator is defined with respect to a so-called cluster operator. And the cluster operator can be expressed in, again, in the level of excitation that you are doing. So one just means Hartree-Fock theory. Then you have single excitations, you have double excitations, you have triple excitations, and so on and so forth. So you can in general write this excitation operator T as a sum of single, double, triple, and so on excitations of your system. So then in this theory, you basically get these operators are defined as a sum over occupied, or again over excitations between occupied and unoccupied states with these so-called amplitudes. And what you need to do is to obtain basically an amplitude equation that lets you optimize the values of those amplitudes. So there are single excitation amplitudes, double excitation amplitudes, triple excitation amplitudes, and so on. So there is a lot of amplitudes if you go to triple excitations, and typically no one actually goes to triple excitations but treats them in a perturbative way to force order of perturbation theory, and that is what is called coupled cluster with single, double, and perturbative triple excitation, so the parenthesis T, which means you do not obtain all these triple excitations, there are just too many of them, but you just treat them effectively to force order of perturbation theory. Okay, so the wave function in coupled cluster is written in this way. Once again, you have the Hartree-Fock wave function typically. So there was a question from the audience actually. This doesn't have to be a Hartree-Fock wave function. This can be any mean field single particle wave function, DFT as well. And then your wave function is written like this. So you have an excitation and de-excitation operator acting on your Hamiltonian. Okay? And so you end up always in the ground state, right? So you excite from the ground state, you return to the ground state.
I thought Kieran rejected the idea that I0 can be DFT orbitals.
So in the quantum chemistry community even, right, a few years ago, there has been a lot of revival of using DFT determinants for coupled cluster calculations, especially for systems that are strongly correlated, that have multi-reference character. And in fact, there are results from Martin-Head-Gordon's group and etc. that for certain classes of systems, DFT wave functions give better agreement with experimental results for things like transition metals and so on. So in principle, right, you can I would say the most conceptually perhaps satisfying or satisfactory approach to correlation is configuration interaction, but it's also the kind of dumb brute force approach. That's why no one really uses it today for many electron systems. But I think conceptually it's very appealing because once again, so you can always define excitations, right, from a ground state. And then you can basically write your wave function as an expansion, right, on, so you have a ground state determinant, for example, Hartree-Fock determinant. But then you can have determinants with effective excitations in them. Once again, you have single excitations, double excitations, triple excitations, and so on. And the level of excitation is, and how many determinants you have, is defined, of course, by the how many orbitals you use to expand your wave function. And if you have a complete expansion, then you have an infinite series, and all you need to do is to obtain this linear expansion coefficients. Now, of course, this is it's easy to say this, but it's much harder to do it because it's a very large linear system, which is not really solvable in practice, and it has a lot of also other practical issues. But in principle, if you can do that, you would get the exact, in a full basis, you would get the exact solution for the many electron wave function. So that's what is called configuration interaction. As I said, it's been used in the past quite a lot to actually get very accurate results for atomic systems. And I think the largest calculations for molecules that have been done perhaps are for water molecule. And I think I remember a few years back, someone was actually trying to parameterize even a potential energy surface of water molecule at the full CI level. I don't know if it actually went anywhere because these are very, very heavy calculations if you want to do the full 6-dimensional potential energy surface. Okay, so in summary, the electronic exchange correlation effects are quantum mechanical phenomena. They are absent in classical mechanics. Hartree-Fock describes exchange or antisymmetry of the wave function, but it has no correlation. Electron correlation energy is quite difficult to calculate. Even MP2 theory is expensive. If you do this in a brute force way, you get n⁵ scaling. Now, people have come up with smart approaches to actually do it in a cubically scaling way, but it's still quite an inexpensive calculation. Coupled cluster theory for many small molecules gets 98% of the correlation energy, right? So what we said is Hartree-Fock gets 98% of the total electronic energy, and then 2% is electron correlation. So CCSD parenthesis T gets 98% of those 2% that are missing in a Hartree-Fock. But sometimes this is not enough, and we discussed transition metal complexes and so on. And in those cases, CCSD parenthesis T is not enough. It's not enough to break the nitrogen dimer because you need to go up to six tuple excitations, for example. And CI, on the other hand, is exact, but it's very expensive, exponentially scaling, and it's a brute force method. There are some newer methods that exploit sparsity in the many electron wave function. You can use that to derive model Hamiltonians, and hopefully this comes with minimal empiricism. And only post-Hartree-Fock methods, and that's the nice part of them, they obey the variational principle, so lower energy typically means better wave function. It's not always the case. So as I said, MP2, for example, is here. MP3 would go down. MP4 would go up, right? So perturbation theory is not variational. Okay, I think I still have time, no? Because we had questions. I think I have 1 hour and 15, no? So I still have 18 minutes. Okay, so I will skip most of this density functional theory because Kieron has talked a lot about this. I will just try to describe what I think are main challenges that density functional theory still have and how we can address those with perturbation theory approaches such as RPA. So we've heard about density functional theory. So just to say a few conceptual words. So instead of the 3n dimensional wave function, of course, as Walter Kohn told us, we can simply work with a three-dimensional object, which does not depend now on the number of particles. And physicists use typically n of r. Chemists prefer to use rho of r to indicate the electron density. So we've already described the Hohenberg-Kohn theorem, density functional theory. So let me skip this. But we have a price to pay because essentially we are coarse graining this complex object that has a lot of physics and chemistry in it. We are coarse graining it to a three-dimensional object. And so, of course, whenever we coarse grain, we lose a lot of physics and chemistry. And the way to recover this coarse graining is to define the quantum mechanical exchange correlation functionals. And of course, the progress in the field has been to incorporate increasingly non-local information in the electron density. As we already saw, LDA is the first approximation, the local density approximation. It only uses local information in the electron density. You can then use the gradient, as for example done in the widely used PBE functional, or you can go to Laplacian of the electron density or the local kinetic energy density as done in meta-GGA functionals. But of course, no one tells you that this expansion will ever go to the exact functional. The exact functional should be functional of the whole electron density of the system and can be extremely non-local. So there's no guarantee, but of course, the way that the functionals are developed is using constraints, sometimes exact constraints, sometimes empirical constraints. And of course, the development has been tremendous for many applications, but not for all applications. And there is, of course, no free lunch. And the two large problems of all existing semi-local functionals is self-interaction error, which means that there is each electron sees itself with a certain energy, which is called the self-interaction energy. And this means that often the orbitals are delocalized, and the electron density is also delocalized. And the second problem is lack of long-range electron correlations. And of course, that means lack of van der Waals, long-range van der Waals interactions. This is illustrated on this slide. So if we now want to study binding between two argon atoms, we know that the long-range van der Waals or dispersion energy has to follow this form. You have the classical cis-6 to the -6 van der Waals term. This is a dipole-dipole interaction, the dipole-quadrupole interaction, and then higher order terms. If we now look at the binding energy as a function of the distance between the two argon atoms, then the reference here is given by CCSD parentheses T. This essentially reproduces experimental data. So this is this red curve. And if we now if we use different functionals, we can get basically anything. Right? So we can get underbinding. So this is Hartree-Fock. As I said, Hartree-Fock would not bind because the only binding here comes from correlation energy, from excitations, from virtual excitations. LDA would overbind quite a bit, and then PBE and TPSS, this is a meta-GGA functional, would underbind, but still would give you a minimum. But something interesting is, if you now zoom into the long distance regime, then in the long distance regime, you see that all density functionals, all semi-local density functionals, follow exactly the same behavior. They decay exponentially with the distance. And that's because the overlap between the densities of the two atoms decays exponentially, and the energy, the exchange correlation energy, follows the same trend. Okay? And so this means that at certain distance all those functionals will underbind with respect to the exact result, which should follow a power law, and instead, so you have to follow an algebraic behavior, instead you follow an exponential decay. This means that you can take any of those functionals and you can correct for this behavior. Now, of course, we are not only interested in argon dimer, we are interested in real systems. So, and if you look at the behavior, at the performance of density of standard semi-local density functionals for many real systems, for example, you realize that intermolecular equilibrium distance are overestimated by quite a lot. most molecules and crystals are unbound. So for example, benzene dimer, if you put it at the equilibrium distance known experimentally, you would get a binding energy of 1.9 kcal per mole, positive 1.9, but couple cluster gives you minus 2.6. So this is quite a large error. Right? If you try to fold the protein using a semi-local DFT functional, you would get a completely wrong structure. Or if you try to study how molecules behave on surfaces, experimentally, large molecules always wet surfaces. Right? But in DFT, they would not do it. Semi-local DFT, of course, not exact DFT. Exact DFT, everything will be fine. And so, in order to go beyond semi-local DFT, we need to introduce explicitly non-local approaches. And we saw today from Jianfeng's talk that there are so-called RPA approaches. And so this means that instead of thinking about the electron density, which is a 3n-dimensional object, we should go to a more generalized non-local function. In this case, this function here is called susceptibility or microscopic susceptibility, or the density response function. And so this is actually a 6-dimensional object in terms of the spatial coordinates, and a 1-dimensional object with respect to time or frequency of the electric field. Okay? And so the essential physics here is that you have a system, this can be atoms or points of the electron density, right? So you have point R1 and point R2, and you are changing the potential at point R1, and you see how the density at point R2 changes as a result of changing the potential here. And that's exactly what this susceptibility function measures. So this is the same thing, right, conceptually as what you already know from constructive and destructive interference of waves. So if you have two stones and you throw them in water and you look at the waves that are formed, you have constructive and destructive interference, and that's exactly the same conceptual physics that happens in the electronic system. Because of fluctuations, you have instantaneous changes of potentials, which change the density. This density change can be positive or negative, right? And that's exactly what this function describes. The frequency here enters because this is a time-dependent phenomenon as well. Right? So there's a time, and you take the difference between two times only, and that's why you do Fourier transform, and you get the frequency here. Okay? And so you have two such functions. You have a so-called non-interacting function. This is lambda equals 0, and you have a partially or fully interacting response function. So non-interacting means that you change the potential here, and the density changes without seeing all the rest of your system. So this is just based on mean field orbitals. And the interacting function means that all the other electrons actually respond to this change of potential at point R1. So if someone gave you this function, which is a 7-dimensional object, right? Well, it's actually a 8-dimensional object because you also need it as a function of lambda. This is called the adiabatic connection parameter. So all you need to do then is to compute this integral. So this integral depends on lambda, on omega, and then this trace means integration over R1 and R2, right? So it's an 8-dimensional integral, right? With spatial frequency and this lambda parameter. And if you can compute this integral, well, you get the exact correlation energy. If your function chi is an exact function. It comes from, well, actually we don't know how to compute the exact one, but if it's good enough, then you can approximate the correlation energy quite well. And so this approach is called the adiabatic connection fluctuation dissipation theorem, or ACFDT, and this comes from statistical physics and from a Lagrangian approach in field theory. So in order to compute the susceptibility, the non-interacting susceptibility, it's defined like this. This is so-called Adler-Weiser formula for the susceptibility, and all it does is basically once again makes excitations from the occupied to unoccupied orbitals. But now you see you don't have a Coulomb potential here in the denominator. You just have a difference between the excited state and the ground state energies, or the occupied and unoccupied energies, plus this frequency factor here. Once you compute this function, you can then solve this Dyson equation for the interacting response function. This is simply, the screening equation. This is exactly the same thing. So this has the screening physics in it because it basically describes how all the other particles or orbitals in your system screen the interaction between two orbitals, right? And if you do this and plug this in here, well, that's it. You get the correlation energy.
Maybe I missed it, but what was Fi and Fj?
These are occupations. So in general, if you have a mean field approach, typically the occupation numbers of the ground state or of the occupied orbitals is 1, and the unoccupied orbitals is 0. But this is written in general because, for example, in metals you would have finite occupations of unoccupied orbitals, and so you generally in this expression you have this occupation numbers. But in the molecular system, this will be ones and zeros. This just means that the ground state, the occupied orbitals do not excite to occupied orbitals, right? And the unoccupied orbitals do not excite to unoccupied orbitals. It's only occupied to unoccupied excitations, right? But if you have not one, so if the occupation numbers in general are not ones and zeros, then you just need to introduce this factor. Okay, so of course, computing this exactly using the full, chi is pretty complicated, right? Because this object by itself is a very complicated, non-local susceptibility function, which depends on this 7 dimensions. And so in order to make those computations efficient, people have came up with all kinds of approaches how to coarse grain this function. So the way to coarse grain is, for example, to introduce 2-point functionals. These are so-called non-local VDW-DF approach, which originally was introduced by Langrest and Lundquist. And the idea is, instead of computing this non-local function, you define it locally at each point in space. And then what you do is you compute interactions between 2 points in space with a certain kernel function that basically mimics how the interaction propagates from A to B. Now this approach is only include pairwise interactions, right? And they are based on a localized representation of this susceptibility function. Instead of doing point-point interactions, you can also do fragment-fragment interactions. So for example, you can define that the polarizability of an atomic projected density has a certain value, and then you can compute this as a pairwise sum over atoms instead of doing a pairwise integral over points of the electron density. Now, of course, all of these approaches are pairwise, and they do not include the screening physics and many-body physics. In order to include many-body physics, right, you need to find a way to coarse grain the susceptibility function. And that's what my group has been doing quite a lot in the past 10 years by developing this so-called many-body dispersion approach, where instead of computing the susceptibility function for the electronic system based on orbitals, we compute a model susceptibility function based on representing atoms as quantum harmonic oscillators. And once you can do this, you can compute this exact formula in a very efficient way by a cubically scaling algorithm, basically. Where instead of electronic degrees of freedom, you have effective oscillator degrees of freedom. Okay, so in the last 2 minutes, let me talk about the last range of approaches here. So we talked about all of these different methods here, but as I already said, there are also semi-empirical approaches that essentially coarse grain degrees of freedom that you have at the DFT level or in the wave function-based methods. And this is, for example, given by semi-empirical quantum chemistry or tight binding approaches. This is something that is perhaps actually, since I don't have time, something can be discussed later in other weeks by, for example, Martin, who is an expert on tight binding. He can tell you exactly what is tight binding is about. So the idea is that you empirically approximate the most expensive integrals in Hartree-Fock correlated calculations by introducing adjustable parameters. And then you adjust those parameters to certain parts of chemical space. In tight binding, instead, you expand the electron density to a certain order in Taylor expansion. So you can do it second or fourth order. And so then all integrals become relatively simple, and you can basically solve the many-body Hamiltonian based on an effective atomic representation of electron density. The weakness is that these methods inherit all the problems of approximate methods, and so long-range correlation is absent, exchange is heavily approximated, and so on. Finally, there are empirical force fields, or classical force fields, and I took this from Wikipedia, where basically you say that there are no electronic degrees of freedom, and you just coarse grain them by simple functional forms. And the way to do this is you separate interactions in terms of bonded interactions and non-bonded interactions. And bonded interactions are, for example, harmonic vibrations of two atoms, harmonic angular terms, and Fourier series for torsional terms. So we have four-body interactions. And the rest is modeled basically most of the times like a Lennard-Jones potential, which represents Pauli repulsion effects and pairwise van der Waals interaction. Okay, so just to summarize, here is basically the strengths, let's say, or the applicability of the different approaches in terms of the system size they can address. So with empirical potentials, classical force fields, you can study up to 100,000 atoms, semi-empirical methods, 10,000 atoms, density functional theory, 1,000 atoms, or more depending if you use linear scaling approaches. These wave function-based methods, today we can do perhaps up to 200 atoms. These are the largest calculations that have been done. And again, full CI is not really widely used for many electron systems. Okay, so that's it. That's all I wanted to tell you. And if you have any further questions, go ahead and ask. Thank you very much.